In this video, we're going to solve an example where we minimize costs with an interior solution. So let's suppose that Ecotech Innovations produces solar panels and their production function is given by 2 L to the 0.5 times K to the 0.5, where L here is units of labor and K is units of capital. We're also told that the price of labor is $50 per unit and the price of capital is $2 per unit. Ecotech Innovation's goal is to produce 100 solar panels. The question we want to answer is, to minimize their costs, how many units of labor and capital should they hire? What do we need to know to answer this question? We need to know the production function, the output goal, as well as the input prices. How are we going to solve this question? By using the tangency condition and the isoquant condition. So just to be really clear here, the tangency condition is guaranteeing that the slope of our isoquant, that ratio of marginal products, is equal to the slope of the isocost line, wage over rent. So this is like an equal slope condition. But at the same time, in a cost minimization problem, we're constrained by our output goal. So you could call this an isoquant condition, or you could call it a production constraint. We need the production Q to equal, in this case, 100 units. So we have two conditions and we have two unknowns. We should be able to solve for the cost minimizing choice of labor and capital using those. It's time for us to solve this question. Here's what we know. Production function, wage, rent, and the output goal of 100 panels. What we're trying to find is the cost minimizing choice of labor and capital. The first thing that we're going to do is we have to find those marginal products so that we can set up the tangency condition. The marginal product of labor is just the partial derivative of the production function with respect to L. So we can write the marginal product of labor as being equal to, let's see, we're going to bring down the 0.5 that L is raised to, and that cancels out the 2. So we get L to the negative 0.5 times K to the 0.5. We also need to find the marginal product of capital. That's going to be the partial derivative of the production function with respect to K. Again, we bring down the 0.5 and it cancels with the 2. So we have L to the 0.5, K to the negative 0.5. With these marginal products, we can set up our tangency condition. The tangency condition has us put the marginal product of labor over the marginal product of capital. So L to the 0.5, K to the 0.5, L to the negative 0.5, K to the 0.5, divided by L to the 0.5, K to the negative 0.5. So that's our ratio of marginal products. And we're going to set that equal to the ratio of prices. The price of labor is the wage. And the price of capital is often referred to as the rent. We'll call this equation 1. We also need to write down that isoquant condition, which if you prefer, you can call a production constraint. So we know we are looking for the lowest isocost line that meets the production goal of 100 panels. We need to write down that production goal. How do we do that? We're simply going to set our production function to L to the 0.5, K to the 0.5 equal to 100. This is forcing us to be on the 100 unit isoquant. From our tangency condition and our isoquant or our production constraint, we can start solving. So I'm going to solve equation 1, the tangency condition for K. It's not going to be a number, it's going to be how K depends on L. This should feel very familiar. It's just like working with a utility function and marginal utilities. So we're going to sort of simplify this thing down. Notice that we have an L to the negative 0.5 in the numerator. If I push that into the denominator, I end up with an L. And I have a K to the negative 0.5 in the denominator. If I move that up to the numerator, I end up with a K. So this can be simplified to K over L is equal to 25. And then solving for K by multiplying both sides by L, I get K is equal to 25L, and I'll call that equation 3. From here, I'm going to take my equation 3 and I'm going to substitute it into my isoquant condition. That's going to allow me to solve for L. Why? Because equation 3 tells me how K depends on L, so I'm able to eliminate K from equation 2, isolating L and solving for the cost minimizing choice of labor. So plugging it in, I get 2 L to the 0.5, and in place of K, I put 25L, and this whole thing is also raised to the 0.5 power equals 100. Now be careful, a really common place for students to make mistakes here is to fail to distribute this 0.5 power to both terms in the parentheses. So if we start simplifying this, we should get 2 L to the 0.5 times 25 to the 0.5, which is 5. And then L to the 0.5 is equal to 100. So be careful about that step there. Don't just leave that 25. 25 should turn into a 5. Now we can combine. 2 times 5 is 10. L to the 0.5 times L to the 0.5 is L, and that equals 100. Dividing both sides by 10, I get that L is equal to 10. So this is my cost minimizing choice of labor, and I'm going to call this equation 4. The final step in the process is to take the fact that labor equals 10 and substitute that into equation 3. Just as a reminder, equation 3 really is just a simplified version of equation 1. So I'm going to take what I know about labor, that it's 10, and I'm going to get that capital is equal to 25 times 10, which is 250. So we've done it. We have determined that the cost minimizing choice of labor and capital is 10 units of labor and 250 units of capital. All it took was a tangency condition and an isoquant condition. If you prefer, you can call that isoquant condition a production constraint.